After studying this module, you shall be able to know the maximum likelihood estimators, learn to derive the slope and intercept maximum likelihood estimator, learn about the properties of Ols and Ml estimators, compare the Oilless and maximum likelihood estimators. Introduction. Maximum likelihood estimators. So far, we have learned how to obtain the sample statistic of slope and intercept using the ordinary least squares method. There is another method available that helps us estimate the sample regression line and is known as the maximum likelihood method. The principle of maximum likelihood is based on the principle that a given outcome occurs because it is most likely to happen. Here we try to maximize the log of the likelihood function, which is the joint probability density function of the given sample of n observations. The maximum likelihood and the ordinary least square estimators of slope and intercept are exactly similar. The two estimators also share a common properties like consistency, efficiency, unbiasedness. However, their estimator for variance is different. Maximum likelihood estimation of simple regression line. To understand this method, let us take a simple example of a pharmaceutical company that has developed a new vaccine to fight dengue fever. The company claims that the vaccine is a success in 85% cases. Success here being defined as the ability of vaccine to cure dengue within 2 days of administration. The initial testing by the Medical Association finds the probability of success to be only 65%. The Food and Drug Ministry has to test the claim and report the correct success rate. The ministry takes a sample of 7 patients and finds the vaccine to be successful in 4 patients. If X is random variable, where X is the number of successes, patients cured after vaccine administration, a binomial distribution. We choose binomial distribution because the alternatives here are dichotomous. That is, either the vaccine would be a success, that is to be able to cure, or a failure, unable to cure. Then the probability of 4 successes out of 7 is given by 1. If we accept company's claim P is equal to 0.85. P brackets NXP is equal to P74.85 minus Cx P to the power x q to the power n minus x minus NCx P to the power x q to the power n minus x, which is equal to 7C4 into 0.85 to the power 4 into 0.15 to the power 3, which is equal to 0.06166. If we accept the Medical Association's claim of P is equal to 0.65, then P74.65 minus 7C4 into 0.65 to the power 4 into 0.35 to the power 3 is equal to 0.2678. P74.65 is equal to 7C4 0.65 to the power 4 0.35 to the power 3. Above, we tried to calculate the likelihood of an outcome under 2 sets of alternatives. We choose the situation that has the maximum likelihood, that is the second alternative. Therefore, in our example, the Food and Drug Ministry agrees to the Medical Association's claim that the probability of success of vaccine is much lower as compared to the pharmaceutical company's claim. The principle of maximum likelihood is hence based on the principle that a given outcome occurs because it is most likely to happen. Generalizing the above principle. Let X be a random variable whose probability distributions depends upon parameters m. Probability density function is Fx given m. a random sample of n independent observations, x1, x2 till xn, is drawn. The joint probability density function of the sample is given by f x1 given m into f x2 given m into f x3 given m till f xn given m. This is the likelihood function denoted by L, m given x, which is equal to pi f xi given m. We try to find the value of L for each value of parameter m and choose that value for which L is the maximum, that is, differentiate L with respect to m such that dL divided by dm is equal to 0 and d square L divided by dm square is less than 0. Rather than maximizing the likelihood function, it is often more convenient to maximize the log likelihood function, that is, function obtained by taking natural logs on both sides. Log of L, m given x, is equal to sigma log of f xi given m. Going back to our PRF, yi is equal to b0 plus b1 xi plus mu I, where as per the assumptions listed for the linear regression model, yi is normally and independently distributed with mean, that is, b0 plus b1 xi brackets e yi divided by xi minus b0 plus b1 xi brackets closed, and variance sigma square. The joint probability distribution function as understood above is f y1 y2 yn given b0 plus b1 xi sigma square, where b0 plus b1 xi is equal to m1 and sigma square is equal to m2 are the two parameters describing our joint probability density function. Also, f y1 y2 till yn given b0 plus b1 xi sigma square is equal to f y1 given b0 plus b1 xi sigma square, f y2 given b0 plus b1 xi sigma square, as y's are independently distributed. F y1 b0 plus b1 xi sigma square is equal to 1 divided by sigma root n pi into e to the power minus half yi minus b0 minus b1 xi whole square divided by sigma square. This is the probability density function of a variable flowing a normal distribution with mean b0 plus b1 xi and variance sigma square. Substituting the value of fyi given in y1 y2 till yn given b0 b1 xi sigma square is equal to 1 divided by sigma root 2 pi e to the power minus half y1 minus beta naught minus beta 1 xi whole square divided by sigma square into 1 upon sigma root 2 pi e minus half y2 minus beta naught minus beta 1 x2 whole square divided by sigma square till 1 upon sigma root 2 pi e to the power minus half y naught minus y3 minus beta naught minus beta 1 x3 whole square divided by sigma square, which is equal to 1 upon sigma n root 2 pi n to e minus half sigma yi minus beta naught minus beta 1 xi whole square divided by sigma square. The above is likelihood function in unknown parameters beta naught plus beta 1 and sigma square. In the maximum likelihood method, we try to maximize this function. It is easier to work with this function by converting it into a log likelihood function. Log of L beta naught beta 1 sigma square is equal to log of brackets open 1 divided by sigma n root 2 pi n e to the power minus half sigma yi minus beta naught minus beta 1 xi whole square divided by sigma square. Log L beta naught beta 1 sigma square is equal to log sigma to the power minus n root 2 pi minus n e to the power minus half sigma yi minus beta naught minus beta 1 xi whole square divided by sigma square. Log L beta naught beta 1 sigma square is equal to minus n log sigma n log root 2 pi is equal to minus half sigma yi minus beta naught minus beta 1 xi whole square divided by sigma square. But our problem remains that PRF, or the population regression function, cannot be constructed. It can only be estimated from sample regression function. As previously, let us depict our SRF as yj is equal to alpha naught plus alpha 1 xi xj plus ej. Earlier, we had used b naught instead of alpha naught and b1 instead of alpha 1. This has been done to avoid confusion. Therefore, b naught and b1 are the Oilless estimators for beta naught and beta 1 slope and intercept term respectively, whereas alpha naught and alpha 1 are maximum likelihood estimators for beta 1 and beta 1 respectively. Rewriting the above equations with maximum likelihood estimates, we get log L is equal to minus n log sigma minus n log root 2 pi minus half sigma yi minus alpha naught minus alpha 1 xi whole square divided by sigma square. Differentiating this, that is log L with respect to the three unknown parameters alpha naught, alpha 1, sigma, and equating it to 0, we get d log L divided by d alpha naught is equal to minus half x 2 by sigma square sigma summation yi minus alpha naught minus alpha 1 xi into minus 1 equal to 0, which is equal to minus 1 by sigma square summation yi minus alpha naught minus alpha 1 xi is equal to 0. Del log L divided by del alpha 1 is equal to minus half x 2 by sigma square summation yi minus alpha naught minus alpha 1 xi into minus xi equal to 0, which is equal to 1 upon sigma square summation yi xi minus alpha naught xi minus alpha 1 xi square is equal to 0. Del log L divided by del sigma is equal to minus n by sigma minus half summation yi minus alpha naught minus alpha 1 xi whole square minus 2 sigma minus 3 is equal to 0, which is equal to minus n by sigma plus summation yi minus alpha naught minus alpha 1 xi whole square divided by sigma to the power 3 equal to 0. Rearranging equation, we get sigma summation yi is equal to n alpha naught plus alpha 1 summation xi. Summation xi yi is equal to alpha naught summation xi plus alpha 1 summation xi square. These are exactly similar to the two normal equations we derived in module 1 while trying to estimate the Ols estimators B0 and B1. Therefore, gives the same value for the maximum likelihood estimators as the Ols estimators. Multiplying equation summation xi and equation 12 by n, we get alpha 1 is equal to n summation xi yi minus summation xi into summation yi divided by n summation xi square minus summation xi whole square. And alpha naught is equal to y bar minus alpha 1 x bar. The Ols estimators B0 and B1 and the ML estimators alpha naught, alpha 1 are similar in value as shown above. This is easily deducible as in Oilless method we try to minimize the sum of the squares of the residuals. Summation ei square is equal to summation yi minus b0 minus b1 xi whole square. Whereas in the ML method we maximize the log likelihood functions. Log L is equal to minus n log sigma minus n log root 2 pi minus half summation yi minus alpha naught minus alpha 1 whole square divided by sigma square. The last term contains the ML estimators and enters with a negative sign. A close look at this numerator of the last term confirms that it is the sum of the squared residuals. Summation ei square is equal to summation yi minus alpha naught minus alpha 1 xi whole square. While trying to maximize this term as we did in Ols method, we are actually maximizing the likelihood function as this term appears with a negative sign. Therefore, the two estimators derived under the two techniques, namely Oilless and ML, turn out to be equal. Properties of the estimator. We have studied in the previous module that the Oilless estimators of slope and intercept are given by B1 is equal to summation xi yi divided by summation xi square, and B0 is equal to y bar minus b1 x bar. The Oilless estimators of the slope can also be written as B1 is equal to summation xi minus x bar into yi minus y bar divided by summation xi minus x bar whole square. Xi is equal to capital Xi minus capital X bar, yi is equal to capital Yi minus capital Y bar. Further, summation xi minus x bar whole square is equal to summation xi square minus x bar square minus 2xi x bar, which is equal to summation xi square plus summation x bar square minus 2 summation xi x bar, which is equal to summation xi square plus n x bar square minus 2 x bar summation xi, as x bar is a constant. Dividing and multiplying the third term by n, we get summation xi minus x bar whole square is equal to summation xi square plus nx bar square minus 2 nx bar summation xi divided by n, equal to summation xi square minus nx bar square. Also, the numerator can be written as summation xi yi is equal to summation xi brackets yi minus y bar summation xi yi is equal to y bar summation xi, as summation xi is equal to 0 because the sum of the deviations from actual mean is always 0. Summation xi yi is equal to summation xi capital Yi. Therefore, the Oilless estimator of slope can be written as B1 is equal to summation xi capital Yi divided by summation capital Xi square minus n x bar square, or summation x capital Yi divided by summation xi square. This estimator is said to be blue, that is best linear unbiased estimator, if all assumptions except for normality assumption of the linear regression model discussed in module 1 hold true. Under the normality assumption, the Oilless estimators are termed as best unbiased estimators, BU instead of blue. Properties of Oilless estimators. The Oilless estimators of slope and intercept are blue if contained in the Gauss-Markov theorem. The following properties hold true. Property number 1. They are a linear function of the dependent variable yi. This can easily be gathered from equation B1 is equal to summation xi capital Yi divided by summation capital Xi square minus n x bar square. Xi divided by summation xi square is equal to Ci, which is equal to C1 y1 plus C2 y2 till Cn yn. Therefore, B1 is a linear function in Yi. They are unbiased estimators. An estimator is said to be unbiased if its mean or expected value is equal to its true value. Expectation of B0 is equal to beta naught and expectation of B1 is equal to beta 1. In order to prove this, let us go back to the value of B1 from equation, that is B1 is equal to summation xi yi divided by summation xi square, which is equal to summation xi minus x bar into yi divided by summation xi square. Substituting the value of yi from the PRF, yi is equal to beta naught plus beta 1 xi plus mu I. Beta 1 is equal to summation xi minus x bar into beta naught plus beta 1 xi plus mu I divided by summation xi square. Beta 1 is equal to beta naught summation xi minus x bar plus beta 1 summation xi minus x bar into xi plus summation xi minus x bar into mu I divided by summation xi square, which is equal to 0 plus beta 1 summation xi square minus xi into x bar divided by summation xi square plus summation xi mu I divided by summation xi square. Summation xi minus x bar is equal to 0 as the sum of deviations from mean is always 0. Rewriting the numerator of the second term in the expression, beta 1 summation xi minus x bar xi divided by summation xi square. Beta 1 summation xi minus x bar in summation xi divided by summation xi square. Multiplying and dividing it by n, beta 1 summation xi minus nx bar square divided by summation xi square, as summation xi divided by n is equal to x bar. Summation xi is equal to nx bar square minus summation xi minus x bar whole square. This expression becomes beta 1 summation xi minus x bar square divided by summation xi square, or simply beta 1. Therefore, B1 is equal to 0 plus beta 1 plus summation xi mu I divided by xi square. As previously put, xi divided by summation xi square was Ci. The above equation becomes B1 is equal to 0 plus beta 1 plus summation Ci ui. Further taking expectations of both sides, expectation of B1 is equal to expectation of beta 1 plus summation Ci expectation of mu I, as Ci is constant, but expectation of mu I as per the assumptions of linear regression model is 0. Expectation of B1 is equal to beta 1. Hence, B1 is an unbiased estimator of beta 1. Simply, we can prove B0 to be an unbiased estimator of beta 0. As we know, B0 is equal to y bar minus beta 1 x bar, substituting the value of y bar as yi is equal to beta 0 plus beta 1 xi plus mu I. Summing both sides and dividing by n, we get summation yi divided by n is equal to beta 0 plus beta 1 summation xi divided by n plus summation mu I divided by n. Y bar is equal to beta 0 plus beta 1 x bar plus mu bar. B0 is equal to beta 0 plus beta 1 x bar plus mu bar minus b1 x bar. Rearranging terms and taking expected value of both sides, expectation B0 is equal to expectation beta 1 minus b1 x bar plus expectation of beta 0 plus expectation of mu bar, which is equal to expectation of beta 1 minus b1 into x bar plus expectation of beta naught as expectation of mu naught is 0, which is equal to expectation of beta 1 minus beta 1 into x bar plus b naught, beta naught as expectation of b1 is equal to beta 1. Therefore, 0 plus beta naught. Hence, expectation of b naught is equal to beta naught. This proves that b naught is also an unbiased estimator of beta naught. The Ols estimators are consistent. Consistency means that as the sample size increases infinitely, the Ols slope and the intercept estimators converge with their true values. That is, as n tends to infinity, b naught is equal to beta naught and b1 is equal to beta 1. Or in other words, as n increases, the variance of b naught and b1 becomes 0. This is a large sample property which does not hold true for small samples. To prove this property, we have to first find the variance of Ols estimators. Variance by definition is the square root of standard deviation. Standard deviation is defined as the root mean square deviations. Therefore, if we wish to find variance of slope estimator b1, it will be the sum of squared deviation from the mean or expected value of b1. Mathematically, variance of b1 is equal to expectation b1 minus expectation of b1 whole square. We know that expectation of b1 is equal to beta 1, variance of b1 is equal to expectation of b1 minus beta 1 whole square. b1 is equal to beta 1 plus sigma summation ci mu I. b1 minus beta 1 is equal to summation ci mu I. Substituting the value in variance b1 above, we get variance b1 is equal to expectation summation ci mu I whole square, which is equal to expectation brackets c1 mu1 plus c2 mu2 till cn mu(n) whole square, which is equal to expectation c1 square mu1 square plus c2 square mu2 square plus c3 square mu3 square till cn square mu(n) square plus 2 c1 c2 mu1 mu2 and it goes on, which is equal to c1 square expectation mu1 square plus c2 square expectation mu2 square plus cn square expectation mu(n) square plus 2 c1 c2 expectation mu1 mu2. As expectation mu1 mu2 is equal to 0, as per assumption of no autocorrelation among error terms. Also, expectation mu1 square is equal to expectation mu2 square is equal to expectation mu(n) square is equal to sigma square as per the assumption of homoscedasticity. Variance of b1 is equal to sigma square brackets c1 square plus c2 square till cn square brackets closed. Variance of b1 is equal to sigma square summation ci square, where xi divided by summation xi square is equal to ci. Squaring and introducing summation ci square is equal to summation xi divided by summation xi whole square. Summation ci square is equal to summation xi square divided by summation xi square into summation xi square is equal to 1 upon summation xi square. Variance b1 is equal to sigma square divided by summation xi square. Now, to prove the consistency property, we find out the limit of the above expression as n tends to infinity. Variance b1 is equal to sigma square divided by n divided by summation xi square divided by n. Taking limits of both sides, limit n tends to infinity, variance b1 is equal to limit n tends to infinity sigma square divided by n divided by limit n tends to infinity summation xi square divided by n. Therefore, both the numerator and denominator are 0, when n tends to infinity. That is, as n increases infinitely, the Oilless estimator's B1 converges towards its true population value beta 1. Same can be said about B0. Property 4. The Oilless estimators are efficient. That is, they have the minimum variance amongst all class of linear estimators. As learnt earlier, B1 is equal to summation Ci yi, where Ci is equal to xi divided by summation xi square. Let us assume any other linear slope estimator that is not an Oilless estimator and represent it by alpha 1 such that alpha 1 is equal to summation di yi, where di is not equal to Ci. Since this alternative linear estimator is also unbiased. Expectation alpha 1 is equal to expectation summation di yi. This is equal to summation di into expectation yi, which is equal to summation di brackets beta naught plus beta 1 xi brackets closed. Substituting expectation of yi is equal to beta naught plus beta 1 xi brackets. Now this is equal to beta naught summation di plus beta 1 summation di xi. For alpha 1 to be unbiased, expectation alpha 1 is equal to beta 1. That is only possible if summation di is equal to 0 and summation di xi is equal to 1. Now variance alpha I is equal to variance summation di yi, which is equal to summation di square variance yi. As per the assumption of homoscedasticity, variance mu I is equal to variance yi is equal to sigma square. Therefore, substituting the value of variance yi, we get variance alpha I is equal to sigma square summation di square. This is equal to sigma square summation di minus xi divided by summation xi square plus xi divided by summation xi whole square. Adding and subtracting the same term, we get sigma square summation di minus xi divided by summation xi square whole square plus sigma square summation xi square divided by summation xi square whole square plus 2 sigma square summation di minus xi divided by summation xi square into xi divided by summation xi square, which is equal to sigma square summation di minus xi divided by summation xi square whole square plus sigma square 1 upon summation xi square plus 2 sigma square summation brackets di xi divided by summation xi square minus xi divided by summation xi square whole square. This is equal to sigma square summation di minus xi divided by summation xi whole square plus sigma square into 1 upon summation xi square plus 2 sigma square summation di xi divided by summation xi square minus summation xi square divided by summation xi square whole square. This is equal to sigma square summation di minus xi divided by summation xi square whole square plus sigma square into 1 upon summation xi whole square plus 2 sigma square brackets 1 upon sigma summation xi square minus 1 upon summation xi square. Since summation di xi is equal to 1, this is equal to sigma square summation brackets di minus xi divided by summation xi square whole square plus sigma square 1 upon summation xi square plus 0. To minimize variance alpha 1, try to equate first term to 0. That is, assume di is equal to xi divided by summation xi square. Then variance alpha 1 is equal to sigma square divided by summation xi square is equal to variance b1. Therefore, the variance of any other linear estimator will always be greater than variance b1. The Oilless estimator, as there is positive term added to it. The variance of alpha 1 would be equal to variance of b1 only in the limiting case, that is 1 di is equal to ci is equal to xi divided by summation xi square, as in case of Oilless estimators. Therefore, one can conclude that Oilless estimators have the minimum variance amongst all class of linear estimators, and therefore they are efficient. Ols estimator of variance is unbiased. In order to understand this, we first need to find out what is the value of the Ols estimator of variance. Going back to our PRF, yi is equal to beta naught plus beta 1 xi plus mu I. Y bar is equal to beta naught plus beta 1 x bar plus mu bar. Also, subtracting the two equations, we get yi minus y bar is equal to beta 1 into xi minus x bar plus mu I minus mu bar. Yi in small terms is equal to beta 1 xi plus mu I minus mu bar. Also from SRF in deviation from we know that E1 is equal to yi minus yi hat is equal to yi minus b1 xi. Substituting the value of yi from equation ei is equal to beta 1 xi plus mu I minus mu bar minus b1 xi. Ei is equal to beta 1 minus b1 brackets closed xi plus mu I minus mu bar. Rearranging, ei is equal to mu I minus mu bar minus b1 minus beta 1 into xi. Summing and squaring both sides, summation ei square is equal to summation mu I minus mu bar square plus summation b1 minus beta 1 square into xi square minus 2 summation mu I minus mu bar into b1 minus beta 1 xi. Rearranging, summation ei square is equal to summation mu I minus mu bar square plus b1 minus beta 1 square into summation xi square minus 2 b1 minus beta 1 into summation mu I minus mu bar into xi. Taking expected value of both sides, expectation summation ei square is equal to expectation summation mu I minus mu bar whole square plus summation xi square e b1 minus beta 1 whole square minus 2 expectation b1 minus beta 1 summation mu I minus mu bar into xi, which is equal to expectation summation mu I square plus n mu bar square minus 2 summation mu I into mu bar plus summation xi square variance b1 minus 2 expectation beta 1 plus summation ci mu I minus beta 1 into summation mu I xi minus mu bar summation xi. This is equal to expectation summation mu I square plus n mu bar square minus 2 n mu bar square plus summation xi square variance b1 minus 2 expectation summation ci mu I into mu I xi as summation xi is equal to 0. This is equal to expectation summation mu I square minus n mu bar square plus summation xi square into sigma square divided by summation xi square minus 2e summation ci mu I square xi as summation ci xi is equal to 1. This is equal to expectation summation mu I square minus 1 by n summation mu I square plus sigma square minus 2 expectation mu I square. This is equal to n sigma square minus 1 upon n into n sigma square plus sigma square minus 2 sigma square. This is equal to n minus 2 sigma square. Expectation of summation ei square is equal to n minus 2 sigma square. Therefore, the Oilless estimator of variance sigma square naught is equal to summation ei square divided by n minus 2. and its expected value may be found out by expectation sigma square naught is equal to expectation summation ei square divided by n minus 2. Expectation sigma square naught is equal to n minus 2 divided by n minus 2 into sigma square, which is equal to sigma square. As expectation of sigma square naught is equal to sigma square becomes an unbiased estimator of sigma square. Properties of maximum likelihood estimators. As we have already discussed, the maximum likelihood estimators are exactly the same as Oilless estimators under normality assumption. Therefore, they possess properties similar to those of Oilless. That is, Ml estimators are consistent. That is, as sample size n increases, the Ml estimators converge towards their true population values. They are efficient. That is, for large n, no other consistent estimator has smaller variance. For large n, they closely follow a normal distribution, even though the distribution from which the sample was drawn may or may not be normal. Property number 4, Ml estimators are obtained from maximum likelihood method, which can be called a large sample method. It therefore has broader application and can be applied to non-linear relationship. Property number 5, the Ols and Ml estimators of variance are however different. The Ols estimator of variance sigma square naught is equal to summation ei square divided by n minus 2 is an unbiased estimator, whereas the Ml estimator of variance sigma square m is equal to summation ei square divided by n is biased. To prove this, consider equation 10, where we differentiated the log likelihood function with respect to sigma. Del log L divided by del sigma is equal to minus n by sigma plus summation yi minus alpha naught minus alpha 1 xi whole square divided by sigma to the power cube is equal to 0. As Ml is equal to Ols, estimators we can write alpha naught is equal to b naught and alpha 1 is equal to b1. Summation yi minus b naught minus b1 xi whole square is equal to n divided by sigma into sigma cube. Sigma square is equal to summation yi minus b naught minus b1 xi whole square divided by n. Maximum likelihood estimator of sigma square into sigma square m brackets is equal to summation ei square divided by n, which is different from the Ols estimator of sigma square bracket sigma square naught is equal to summation ei square divided by n minus 2. Ols expectation of sigma square m is equal to expectation of summation ei whole square divided by n. Expectation of sigma square m is equal to 1 by n into expectation sigma ei square is equal to n minus 2 divided by n into sigma square. As expectation of summation ei square is equal to n minus 2 sigma square from equation sigma square minus 2 by n sigma square. Expectation of sigma square m is not equal to sigma square, as there is something subtracted from it, lending it a downward bias. But as n tends to infinity, 1 by n tends to 0. Therefore, the second term reduces to 0, and therefore expectation of sigma square m is equal to sigma square. Ml estimator of variance becomes unbiased only when n is large. Therefore, as we have already discussed, the Ml are exactly same as the Ols estimators under normality assumption. Therefore, they possess properties similar to those of Ols estimators. Comparison between Ols and Ml estimators. Under the assumptions of linear regression model stated in module 1, we have proved that Ols estimators are blue. They are unbiased, efficient, that is minimum variance, under any sample size. As this sample size approaches infinity, they are also consistent. If the normality assumption is also added to the usual set of assumptions under CLRM, then the Oilless estimators become blue in the entire range of unbiased estimators, whether linear or not. Also, if we assume that the error term is normally distributed, the Oilless and Ml estimators of intercept and slope are similar. These estimators are best unbiased estimators when the sample size is large, that is, as n tends to infinity. These are therefore referred to as large sample estimators. The Ols estimators of variance given by sigma square naught is equal to summation ei square divided by n minus 2 is different from ml estimator of variance, that is sigma square m is equal to summation ei square divided by n. This estimator is biased, whereas the former has been proved to be unbiased. Further, it has been shown that as n increases, ml estimator of variance also becomes unbiased. Summary. The maximum likelihood estimators are obtained by maximizing the log likelihood function. The ML estimators of slope and intercept are similar to the estimators obtained after using the Oilless method. Oilless estimators are blue, that is, they are efficient, consistent, and unbiased and linear. The ML estimator is also consistent, efficient, normally distributed, and often called large sample estimators. The ML estimator of variance, however, differs from its Oilless counterpart. The former is biased, whereas the latter is unbiased.